close your eyes, if you are able, and let the weight of the day settle gently into the mattress beneath you. Let your shoulders fall, let your jaw unclench, let the small muscles around your eyes soften and release. There is nothing you need to do right now. There is nowhere you need to be. The only thing asked of you in this quiet and darkened moment is to breathe slowly and to listen and to let the words drift over you like warm water, carrying you somewhere far away and long ago. We are going to travel together tonight, you and I, into the slow and fascinating story of a small plant, unremarkable at first glance, growing quietly along the roadsides and riverbanks of ancient Africa. Its broad leaves catching the afternoon light, its seeds hanging in clusters of soft red and brown, looking for all the world like harmless beads, like something a child might collect and place in a pocket. And yet within those seeds, there rests one of the most quietly extraordinary substances the natural world has ever produced. We will not rush this story. We will take it slowly, as all good stories deserve to be taken, pausing here and there to let the details settle into you, to let the names and the dates and the places find their way gently into your mind, before the mind itself begins to soften towards sleep. If this voice helps you rest, consider subscribing to Plague Lullaby, but only if you are still awake to hear that suggestion. And now, let us begin at the beginning, as all good bedtime stories must, in a time so distant that the very concept of a poison derived from a plant was not a matter of science, but of quiet, ancient observation, passed from generation to generation in the manner of all early human knowledge, carefully, slowly, with great attention paid to what the natural world was willing to teach. The castor plant, known to botanists as Ricinus communis, is a species of considerable antiquity in the human story, and its relationship with our kind stretches back thousands of years before anyone possessed the language of chemistry or the tools of the laboratory to explain what it was doing or why. The word ricinus is itself Latin, meaning tick, a name given because the mottled oval seeds of the plant bear a passing resemblance to the body of a particular species of European tick, and there is something almost poetic in the fact that a plant so deeply woven into human history should carry a name drawn from such a small and ordinary comparison. The plant is native to the tropical regions of East Africa, particularly the highlands around what we now call Ethiopia, where it grew in the disturbed soils along riverbeds and at the edges of cultivated land, thriving in the conditions that human settlement tends to create. The ancient Egyptians knew this plant well, and archaeologists have found castor seeds in tombs, dating back more than 4,000 years, seeds placed alongside the bodies of the dead as objects of practical value because the oil pressed from those seeds burned cleanly in lamps and was used to anoint the skin and to treat ailments of many kinds. Over the centuries and millennia that followed, the castor plant traveled slowly outward from its native range, carried by traders and travelers, and the gradual movement of human populations across the Mediterranean world and beyond, until it had established itself across Arabia and Persia and India, and eventually throughout the tropical and subtropical regions of the entire globe. In India, traditional Ayurvedic medicine incorporated the castor plant into a wide range of preparations, valuing it as an anti-inflammatory agent, as a treatment for skin conditions, as a laxative, and as an abortifacient, and practitioners who worked with it over generations accumulated a practical understanding of the fact that the plant, in certain forms and certain doses, could cause considerable harm. It is worth noting that throughout all of this long early history, the oil pressed from castor seeds was considered separately from the seeds themselves, because the oil was, and remains, essentially safe for human consumption, used medicinally around the world, and even listed in pharmacopoeias of the modern era, while the seeds and the residual material left behind after pressing contained something altogether different, something that would not be named or understood for many centuries to come. The ancient Greeks and Romans both had some knowledge of the castor plant, and writers of natural philosophy and medicine in the classical period made mention of its properties, though their understanding was necessarily incomplete, filtered through the lens of a medical tradition that explained illness and healing in terms of humors and elemental forces rather than molecules and cellular mechanisms. Meanwhile, across the Islamic world during the medieval period, scholars who translated and expanded upon the Greek medical tradition continued to record observations about the plant, noting that the seeds in particular were dangerous in ways that the oil was not, though the precise nature of that danger remained beyond the reach of the explanatory tools available to them at the time. And so the castor plant moved through the centuries in this quiet way, simultaneously useful and dangerous, grown in gardens and fields across half the world, its seeds harvested for oil, its residue composted or discarded, while the thing hidden within those seeds, the substance that would one day carry the weight of assassinations and bioterrorism, fears and centuries of scientific inquiry, waited patiently for the particular moment in history when human knowledge would finally be ready to perceive it. The 16th and 17th centuries brought the castor plant into the gardens of England, where it was grown as an ornamental curiosity, as much as for any practical purpose. Its large, dramatically lobed leaves and its striking clusters of reddish seeds, making it a plant that drew the eye in any garden where it appeared. During this period, the broader European tradition of herbalism was gradually giving way to something more systematic, more observational, more willing to perform deliberate experiments, rather than simply record inherited wisdom, and the natural world in all its variety was being catalogued and examined with a new and particular attention. Physicians and apothecaries of the era had a general awareness that certain plants could harm as well as heal, and the castor plant was among those that appeared in lists of plants requiring careful handling, though the specific mechanism of its toxicity was no more understood in the 17th century than it had been in the time of the ancient Egyptians. It is worth noting that during this same period, the Atlantic slave trade was causing the forced migration of millions of people from West and Central Africa to the Americas. And with those people came knowledge of plants and their properties, including the castor plant, which had long been familiar in the agricultural traditions of the African continent, and which took root and naturalized in the warmer regions of the New World with remarkable ease. By the 18th century, castor oil had become a significant commercial product in both Europe and the Americas, valued as a lubricant, as a medicinal preparation, and as a raw material for a range of industrial processes, and large plantations in India, Brazil, and parts of the southern United States were dedicated to its production. The seeds were pressed, the oil was extracted and refined, and bottled and shipped, and the residual seed cake left behind, after pressing, was considered a byproduct of limited value, sometimes used as a high nitrogen fertilizer for agricultural fields, sometimes simply discarded. What no one yet fully understood was that this seed cake, this quiet byproduct of a prosperous commercial industry, contained within it a substance of extraordinary and unsettling potency, a protein of such precise and devastating biological action that it would, in time, become the subject of both military research and scientific fascination in equal measure. During this period, the tools and concepts needed to understand what that substance was and how it worked did not yet exist, because the science of proteins and of cellular biology was itself still in the earliest stages of development, and the understanding of how disease operated at the level of the cell lay several generations in the future. And so the castor plant continued its quiet commercial career through the 18th century. Grown in vast quantities, pressed for its oil, its seed cakes spread across farmers' fields, while the hidden thing within it remained hidden, patient, waiting, as it had waited for thousands of years, for the particular convergence of scientific curiosity and laboratory technique that would finally bring it into the light. That convergence arrived in the year 1888, in a city that was then known as Dorpat, in the Baltic region of what is now Estonia, in the laboratory of a professor named Rudolf Kobert at the Imperial University of Dorpat. It was in that laboratory, amid the quiet routine of academic research, that a doctoral student named Peter Hermann Stillmark undertook the work of his thesis, which concerned itself with the chemical properties of castor bean seeds, and specifically with the question of whether those seeds contained something beyond the oil, something that might explain the long-observed toxicity of castor bean preparations that had not been refined into pure oil. Stillmark's approach was methodical and patient, as the work of good science must be, and over the months of his investigation, he developed a series of extraction procedures that allowed him to isolate a substance from the seeds that was not the oil, not any of the known alkaloids that had been previously identified in plant materials, but something of a different and unfamiliar character altogether. The substance he isolated was a protein, though the language and conceptual framework that would fully describe what a protein was and how it behaved in biological systems were themselves still being developed in the scientific community of the late 19th century, and Stillmark described what he had found in the more provisional language of his time, calling it a ferment, a term that carried some of the meaning we would today associate with an enzyme. He named the substance ricin, drawing the name from the genus name of the plant itself, and he described in his doctoral thesis the extraordinary toxic properties he had observed when the extracted substance was administered to experimental animals, noting that it caused agglutination of red blood cells and rapid death even in very small quantities. This discovery was remarkable enough in itself, but it carried an additional significance that was recognized only gradually over the years and decades that followed, because ricin turned out to be the first member of a class of carbohydrate-binding proteins that scientists would eventually call lectins, and Stillmark's work is therefore considered the founding moment of an entire branch of biochemistry known as Yapayit lectinology. The University of Tartu, as Dorpat was renamed following Estonian independence, crafted a commemorative medal in 1988 to mark the centennial of that discovery, a quiet acknowledgement of the significance of what had been done in that 19th century laboratory by a methodical young scientist working under the guidance of his professor. Over the next several years, following Stillmark's thesis, other researchers in Europe began to examine ricin more closely, attempting to understand its chemical nature and to measure its toxic potency with greater precision, and the results of those early investigations were striking enough to attract the attention of scientists working in fields well beyond the original scope of academic chemistry. It is worth noting that the late 19th century was also the period in which the germ theory of disease was being established, in which the work of Louis Pasteur and Robert Koch was reshaping the entire understanding of infection and immunity, and it was within this larger context of biological discovery that ricin took its place as one of the most studied and most troubling of the natural world's chemical offerings. And in the quiet university town on the Baltic, the doctoral student who had made that discovery had no way of knowing, as he completed his thesis and received his degree, that the substance he had named and described would still be attracting attention more than a Siege century later, still being studied in laboratories around the world, still carrying the weight of its extraordinary and troubling properties into an era he could not have imagined. The years that followed Stillmark's discovery were years of gradual scientific consolidation as researchers across Europe and eventually North America worked to characterize ricin more fully and to understand the manner in which it caused the effects that Stillmark had first observed. One of the most important early contributions to this growing body of knowledge came from Paul Ehrlich, a German physician and scientist whose work on the immune system would eventually earn him the Nobel Prize in Medicine in 1908, and who turned his attention to ricin in the early 1890s as a subject for experiments in immunization. Ehrlich's investigations demonstrated that animals injected with very small, carefully controlled doses of ricin could develop a tolerance to the substance over time, building up what he called anti-toxin activity in their blood. And these experiments became some of the earliest studies in the emerging science of immunology, contributing to Ehrlich's broader theoretical framework for understanding how the body responds to and defends against foreign substances. There is something quietly remarkable in this aspect of the history, in the fact that a substance so profoundly toxic became one of the tools through which the fundamental principles of immunity were first worked out, that ricin's very dangerousness made it a useful experimental subject for the researchers who were laying the foundations of modern medicine. Meanwhile, during this same period of the 1890s, another set of observations was being made that would prove consequential for the later history of ricin as a potential weapon, as military chemists and physicians in Europe and North America became aware of the substance's extraordinary potency and began to consider, in the cautious and abstract terms of academic speculation, what it might mean to have access to a material of such potent biological action. The specific mechanism by which ricin killed cells was not yet understood, because the science of molecular biology that would eventually explain that mechanism in precise detail did not yet exist. But the empirical fact of ricin's lethality was established clearly enough in the laboratory animal experiments of the late 19th century that its potential as something other than a scientific curiosity was apparent to those who thought about such things. It is worth noting that the late 19th century was also the period in which the international community was beginning to grapple for the first time with the legal and ethical questions surrounding the use of toxic materials in warfare, culminating in the Hague Convention of 1899, which placed restrictions on the use of certain categories of weapons in armed conflict between nations, though the specific question of biological toxins such as ricin occupied a somewhat ambiguous position in the international legal frameworks of the time. During this period, the castor plant itself continued its quiet commercial career, its oil in demand for industrial and medicinal purposes, its seeds pressed in facilities across India and Brazil and elsewhere, with little public awareness of the fact that the residual material from this entirely ordinary commercial process contained one of the most potent natural toxins known to science. The distance between the everyday world of castor oil commerce and the rarefied world of laboratory toxicology was, in those years, very great, and the average person who took a spoonful of castor oil as a laxative, or who used it to lubricate a household mechanisms, had no particular reason to think about what lay in the pressed out seed cake being composted in the fields behind the processing facility. And so the first decade or two after Stillmark's discovery passed in this way, with ricin gradually becoming better known within the specialized world of scientific research, accumulating a small but significant body of literature, while remaining entirely unknown to the vast majority of people who encountered the castor plant in any of its everyday forms. The turn of the 20th century brought with it an acceleration of interest in ricin that was driven not only by the pure scientific curiosity of academic researchers, but also by the growing awareness among military planners in several nations that the new sciences of chemistry and biology were creating possibilities that earlier generations of soldiers and strategists could not have imagined. The First World War, which began in 1914 and consumed Europe in a conflict of unprecedented scale and industrial brutality, became the first large-scale conflict in which chemical weapons were used deliberately and systematically, with chlorine gas, phosgene, and eventually mustard gas deployed by both sides, with devastating consequences for the soldiers exposed to them. In this context, the question of whether biological toxins such as ricin might be weaponized was one that military researchers in several countries found themselves considering with increasing seriousness, and the United States War Department is documented to have studied ricin as a potential chemical warfare agent as early as 1918, toward the final months of that first great conflict. The specific proposals under consideration involved the incorporation of ricin into artillery shells or other delivery mechanisms with the intention of dispersing the toxin over enemy positions in a form that combatants might inhale or absorb through the skin, though the technical challenges of this approach were considerable, and the war ended before any of these proposals were put into operational practice. During the period between the two world wars, the international community made further attempts to restrict the use of chemical and biological weapons, most notably through the Geneva Protocol of 1925, which prohibited the use of such weapons in warfare, but which did not prevent nations from developing and stockpiling them, a distinction that would prove consequential in the years that followed. In the laboratories of several nations during the 1930s and 1940s, research into ricin as a potential weapon continued, with scientists working to understand not only the toxin's biological properties, but also the technical questions of how it might be produced in sufficient quantities and delivered in a form that would make it practically effective as a weapon of war. The United States and Great Britain both conducted research programs involving ricin during the Second World War, with the British program in particular making advances in the production of ricin in a form suitable for use in munitions, and experiments were conducted at various facilities to characterize the toxin's behavior under different conditions of temperature, humidity, and exposure. It is worth noting that during this same period, the broader science of protein chemistry was advancing rapidly, driven by the availability of new laboratory techniques and by the enormous investment in biological research that the war effort had stimulated, and researchers working on ricin were beginning to develop a more detailed, though still incomplete, picture of the chemical structure of the toxin and the manner in which it interacted with living cells. The conclusion of the Second World War in 1945 brought a pause to the most intensive phase of military ricin research, as attention shifted to other priorities and as new international agreements sought to place limits on weapons of mass destruction. But the knowledge that had been accumulated during the war years did not disappear, and it continued to inform research programs in various countries throughout the Cold War period that followed. And in the quiet time that followed the war, in laboratories that were no longer focused on immediate military application, scientists continued to study ricin for its own sake, drawn by the genuinely extraordinary nature of its biochemistry, by the precise and almost elegant mechanism through which it accomplished the interruption of life at the cellular level. The mechanism by which ricin kills cells is one of the more remarkable examples of molecular precision in the natural world, and understanding it requires a brief consideration of some of the fundamental processes of life at the cellular level, though we will move through this territory slowly and gently, without urgency, pausing as needed to allow the concepts to settle into place. Every living cell, whether it is a cell in the lining of the human intestine, or a cell in the liver, or in the walls of a blood vessel, depends for its survival on a continuous process of protein synthesis, the manufacturing of new protein molecules, to replace those that have worn out and to carry out the countless tasks of cellular maintenance and function. This process of protein synthesis takes place on structures within the cell called ribosomes, which serve as the molecular machinery that reads the instructions encoded in the cell's genetic material and uses those instructions to assemble amino acids into the specific protein molecules that the cell requires. Ribosomes are, in a sense, among the most essential pieces of equipment in the cellular factory. And without functioning ribosomes, a cell cannot manufacture the proteins it needs to survive, and without those proteins, the cell's functions fail, and the cell itself dies. Ricin's action on the cell is directed precisely and specifically at these ribosomes, and it accomplishes its work through the two distinct components of its molecular structure, known to scientists as the A chain and the B chain, each of which has a distinct and necessary role in the overall mechanism of toxicity. The B chain of the ricin molecule is what allows it to gain entry to the cell in the first place, and it does this by binding to carbohydrate structures on the surface of the cell membrane, structures containing a sugar called galactose that appears on the surfaces of virtually all mammalian cells, which means that ricin is capable of entering almost any cell in the body, rather than being limited to a specific cell type. Once the B chain has bound to the cell surface, the entire ricin molecule is taken into the cell through a process called endocytosis, in which the cell membrane folds inward around the bound molecule and carries it into the cell's interior, inside a small membrane-enclosed compartment. From there, the ricin molecule travels through a remarkable series of internal compartments, moving from the early endosomes to the Golgi apparatus, and then into the endoplasmic reticulum, a journey that takes the toxin progressively deeper into the cell's interior machinery, until it reaches the point where the A chain can be released into the cytosol, the fluid interior of the cell where the ribosomes carry out their work. Once the A chain reaches the cytosol, it performs the specific and irreversible action that constitutes ricin's lethal effect, which is the removal of a single adenine residue from a specific location on the ribosome's RNA component, a precise molecular cut that permanently disables the ribosome and prevents it from participating in protein synthesis. It is worth pausing on the extraordinary economy of this action. The fact that a single molecule of the ricin A chain, once it has reached the cytosol, is capable of inactivating thousands of ribosomes per minute, working through the cell's interior with a quiet and systematic thoroughness that is, from a purely biochemical standpoint, a remarkable example of enzymatic efficiency, even as its consequences for the living organism are deeply and irrevocably harmful. The clinical picture of ricin poisoning in a living person is shaped by the route through which the toxins enters the body and the three principal routes of exposure, which are ingestion through the digestive system, inhalation into the lungs, and injection directly into the bloodstream or tissues. Each produce a somewhat different progression of symptoms, though all three ultimately converge on the same fundamental process of cellular disruption and organ failure, if the dose received is sufficient to cause serious harm. In cases of ingestion, which represent the large majority of documented historical cases of ricin poisoning, the clinical course typically begins within a few hours of exposure, with the onset of nausea, vomiting, and abdominal discomfort as the toxin begins to act on the cells of the gastrointestinal lining. During this initial phase, the person affected may be aware only of what seems to be a severe gastrointestinal illness, without any reason to suspect that something more serious is taking place at the cellular level throughout the body, and this period of apparent recovery from the most immediate symptoms can be deceptive, creating the impression that the worst has passed. Over the next 1 to 3 days, as the toxin continues its work at the cellular level in tissues throughout the body, the clinical picture typically becomes more serious, with evidence of dysfunction in multiple organ systems, including the liver, the kidneys, and the cardiovascular system, as the accumulation of cellular damage in these tissues begins to manifest as measurable abnormalities in blood tests and clinical examination. Medical practitioners in that era, whether of the 19th century or the early 20th, had limited tools for understanding what was happening in such cases. And the clinical records from the earlier periods of ricin's history describe the progression of severe castor bean poisoning in terms that reflect the medical knowledge of the time, noting the failure of pulse and respiration, the accumulation of fluid in tissues, the progressive loss of consciousness, without the ability to attribute these observations to the specific molecular mechanism that modern biochemistry has since elucidated. It is worth noting that the lethality of ricin by ingestion is considerably lower than its lethality by injection or inhalation, because the gastrointestinal tract absorbs the toxin imperfectly, and the digestive process degrades a portion of the protein before it can be absorbed, which means that a person who swallows castor beans may receive a dose that causes severe illness without necessarily receiving a dose sufficient to cause death, depending on the number of beans consumed, the manner in which they were prepared, and individual factors relating to the person's health and the condition of their gastrointestinal tract. Historical medical literature records more than 1,000 cases of ricin poisoning from the ingestion of castor beans since the late 19th century, a body of clinical observation that has allowed physicians to characterize the typical course of such poisoning with some precision, even in the absence of any specific antidote or targeted treatment. The management of castor bean poisoning has historically been supportive in nature, focused on maintaining fluid balance, supporting organ function, and managing the secondary consequences of severe gastrointestinal illness, and this remains largely true in modern medicine. because despite decades of research, no specific antidote to ricin has yet been approved for clinical use. A fact that gives the substance a continuing relevance in discussions of both medical toxicology and biosecurity. Over the period from the late 19th century through to the present, the documented cases of ricin poisoning have occurred in a variety of contexts, ranging from accidental ingestion by children who encountered castor bean seeds in gardens or along roadsides, to deliberate ingestion in cases of self-harm, to the very small number of cases involving intentional poisoning of others, each category presenting its own particular challenges for the medical practitioners called upon to respond. And through all of these varied circumstances, the underlying biology has remained consistent. The same molecular mechanism first characterized in the laboratories of the late 19th century, continuing to operate with the same quiet precision in every case. The ricin A chain performing its specific and irreversible action on the ribosomes of whatever cells it happened to reach, indifferent to the circumstances that had brought it to that particular body in that particular moment. There is a particular case in the history of ricin poisoning that stands above all others in terms of its historical significance and its cultural resonance, a case that brought the name of this obscure laboratory toxin to the attention of the general public for the first time, that wove it into the narratives of Cold War espionage and political violence, and that demonstrated with tragic clarity the consequences of ricin's action in a living human being exposed to a precisely administered dose. The case concerns a man named Georgy Markov, a Bulgarian writer and playwright, who was born in Sofia in 1929, and who came to represent, in the estimation of many observers, one of the most compelling literary voices of his generation in Eastern Europe, a writer whose work engaged honestly and critically with the social and political realities of life under the communist regime that governed Bulgaria during the post-war decades. Markov's literary success in Bulgaria during the 1960s gave way to increasing friction with the authorities as his work became more openly critical of the regime, and in 1969 he left Bulgaria for the West, first making his way to Italy, and eventually settling in London, where he found employment as a broadcaster with the BBC World Service and with Radio Free Europe, organizations that provided a platform for commentary on political and cultural affairs in Eastern Europe, directed at audiences behind the Iron Curtain. Over the years that followed his defection, Markov's broadcasts became widely listened to within Bulgaria, where they were received by audiences who had access to shortwave radio receivers, and who valued the perspective of a fellow Bulgarian speaking from outside the constraints that limited public discourse within the country, and his commentaries on Bulgarian political and social life were considered sufficiently threatening by the Bulgarian authorities that they took the extraordinary step of requesting assistance from the Soviet security services in planning and executing an operation to silence him. It is recorded that there were at least 2 earlier attempts on Markov's life before the one that ultimately succeeded, including an incident in Munich in the spring of 1978 when he was visiting colleagues at Radio Free Europe, and someone introduced a toxin into his drink at a dinner held in his honor, though that attempt did not result in serious harm, and Markov himself may not have been certain at the time that it was a deliberate poisoning. The attempt that succeeded came on the 7th of September 1978, on Waterloo Bridge in London, on an ordinary morning when Markov was making his way to work at the BBC, a morning that in its initial aspects must have seemed entirely unremarkable. The grey light of an early autumn day in the city, The sounds of traffic and the movement of people across the bridge, the ordinary texture of a weekday commute. What Markov experienced at that moment, as he recalled it in the brief time remaining to him, was a sudden, sharp pain in his right thigh, as though something had stung him, and when he saw a man retrieving an umbrella from the pavement nearby, who apologized briefly and then moved away quickly, crossing the road to enter a waiting taxi. Markov continued to work that day, though the pain in his leg persisted, and he noted a small red mark at the site of the apparent sting, and it was only as the day progressed, and he began to feel increasingly unwell, developing a fever and a sensation of spreading illness, that he began to wonder whether something more significant had occurred on Waterloo Bridge that morning. He was admitted to hospital the following day, as his condition continued to deteriorate, and over the 3 days that followed his admission, the medical team caring for him observed the progressive failure of his body's systems, a clinical course that the physicians of the time found difficult to explain with the diagnostic tools available to them, because the specific agent responsible for his condition was not yet identified, and the pattern of his illness did not correspond clearly to any known natural disease. Georgy Markov died on the 11th of September, 1978, 4 days after the incident on Waterloo Bridge, and he was 49 years old, and the investigation that followed his death would eventually lead to the discovery of a remarkable and sobering piece of forensic evidence that explained everything and that placed the science of ricin at the center of an international story that would be told and retold in the decades to come. The post-mortem examination of Georgy Markov's body was conducted by pathologists in London who were aware that the circumstances of his death were deeply unusual and who approached the examination with the particular care warranted by a case that might have implications beyond the purely medical. In the course of that examination, the pathologist discovered, embedded in the tissue of Markov's right thigh at the precise location where he had felt the sudden pain on Waterloo Bridge, a tiny metallic pellet of extraordinary precision, a sphere measuring approximately 1.7 millimeters in diameter, fabricated from an alloy of platinum and iridium, materials chosen for their resistance to corrosion and their biological inertness, with 2 small holes drilled through its center in the form of a cross. The pellet had been designed, with considerable technical sophistication, to function as a delayed release vehicle for a toxic payload. The 2 small chambers within it, capable of holding a quantity of ricin, small enough to be undetectable to the naked eye, but large enough, given the extraordinary potency of the toxin, when delivered directly into the tissues of the body, to cause the lethal dose that had been so precisely calculated. The mechanism of delivery had been a device disguised as an ordinary umbrella, modified with an internal mechanism capable of firing the pellet into the tissue of a person standing at close range, with the force of a compressed gas charge, a weapon of considerable ingenuity that left no immediately obvious trace of its operation, the pellet being far too small to be noticed without deliberate and careful examination of the wound site. The discovery of the pellet and the subsequent analysis of its contents and construction provided the forensic basis for identifying ricin as the agent responsible for Markov's death, a conclusion that was reached in collaboration between the British police, the British government's defence research establishment at Porton Down, and experts in toxicology who had the specialised knowledge necessary to recognise what had been used and to characterise its properties. The investigation into the circumstances of the assassination pointed strongly toward the involvement of the Bulgarian State Security Service, known by its acronym DS, and it was widely assessed by Western intelligence agencies that the operation had been carried out with the knowledge and technical assistance of the Soviet KGB, which had both the expertise and the resources to design and manufacture the specialized weapon that had been used. In the years following the assassination, as details of the case became more widely known, the story of Georgy Markov and the poisoned umbrella became one of the defining narratives of Cold War espionage, a story that illustrated with particular vividness the lengths to which authoritarian states might go to silence voices of dissent and the extraordinary technical capabilities that intelligence services of the period had developed. The Bulgarian government, operating under the communist regime that had ordered the assassination, initially denied any involvement in Markov's death, and it was only after the political transformations of 1989 and 1990 that Bulgarian authorities began to acknowledge the historical record with greater candor, though the investigation into the case continued for decades without resulting in any criminal prosecution. For the scientific community, the Markov case had a significance beyond its political and historical dimensions, because it provided the first documented case in which reason had been deliberately used to kill a specific individual, and the detailed forensic and medical records generated by the investigations became an important source of clinical information about the effects of ricin administered by injection in a human being. The case also drew public and governmental attention to the potential for naturally derived biological toxins to be used as instruments of targeted assassination, or, more broadly, as weapons in the hands of state or non-state actors with malicious intent, a concern that would grow substantially in the decades following the end of the Cold War, as the accessibility of information about such substances increased, and as biosecurity became a more prominent feature of public health and national security discussions. And in London, on Waterloo Bridge, the ordinary grey morning of the 7th of September, 1978, remains a moment marked by the quiet intersection of Cold War politics and the ancient chemistry of a plant that had been growing along the riverbeds of East Africa for thousands of years, its seeds carrying their hidden cargo through all that long time, waiting for the particular and terrible use to which they were finally put on that bridge on that morning in that city. The Cold War, which settled over the world in the years following the conclusion of the Second World War, was in many ways a conflict conducted not with armies and artillery in open fields, but with information and deception, and the quiet, patient accumulation of technical capabilities that might never be used, but whose existence shaped the behavior of nations and the calculations of strategists in ways both visible and invisible. It was a conflict in which the laboratories of both the Western powers and the Soviet Union and its allies became theatres of a kind of scientific competition, each side seeking to develop capabilities that the other did not possess, or to match capabilities that the other was known or suspected to have. And within this broader context of scientific militarization, the study of biological and chemical agents occupied a significant and deeply consequential place. The Soviet program of biological weapons research, which came to be known in the West, only gradually and imperfectly during the Cold War years, and which was disclosed more fully only in the early 1990s through the testimony of defectors and the opening of some archival records, was a program of extraordinary scale and ambition, employing tens of thousands of scientists and technicians across dozens of facilities spread throughout the Soviet Union, conducting research into a wide range of biological agents that included bacteria and viruses, and toxins of various kinds. Within this vast program, ricin occupied a particular niche, valued not for the mass casualty potential that characterized some of the more fearsome agents under investigation, but for the precision it offered as a tool of targeted action against specific individuals, a quality that made it particularly attractive to intelligence services engaged in the kind of operations that required the elimination of particular persons rather than the indiscriminate deployment of force. The Bulgarian State Security Service's use of ricin in the Markov assassination was not an isolated improvisation, but rather an expression of a larger technical capability that had been developed with Soviet assistance. And in the years following 1978, intelligence analysts in the West worked to understand the full scope of what the Soviet bloc had developed in terms of specialized assassination technologies. Meanwhile, in the United States and in Britain, research programs that had their roots in the Second World War era continued to examine ricin and related toxins, though the specific focus and classification level of these programs shifted over the years. In response to changing priorities, changing international agreements, and the gradual evolution of scientific understanding that was making the biochemistry of these substances more precisely comprehensible. The Biological Weapons Convention of 1972 represented an important milestone in international efforts to restrict the development and stockpiling of biological agents for military purposes, and both the United States and the Soviet Union were among the original signatories to that agreement. Those subsequent revelations about the Soviet program made clear that the convention had been violated on a substantial scale throughout the period of its existence. It is worth noting that the Biological Weapons Convention, unlike later agreements in related areas, did not include provisions for on-site inspection or verification, a significant omission that left the treaty dependent on the good faith of its signatories rather than on any mechanism of independent confirmation, a weakness that the history of Soviet biological weapons development would ultimately make painfully apparent. During this period of the 1970s and 1980s, the broader scientific community's understanding of ricin's molecular mechanism was advancing steadily, driven by the application of new biochemical and structural techniques that were allowing researchers to visualize and characterize the toxin's components with increasing precision. And this growing body of knowledge was simultaneously informing both the defense research programs that sought to develop protective measures and the medical research programs that were beginning to explore whether ricin's extraordinary cytotoxic potency might somehow be turned toward therapeutic ends. And through all of this period, the castor plant itself continued its quiet commercial existence, growing in fields across India and Brazil and China and parts of Africa and the Americas, its seeds harvested by workers who, in many cases, had no particular awareness of the biochemical drama that had attached itself to the substance. Their labor was helping to produce, the plant indifferent, as always, to the uses that human ingenuity had found for its most extraordinary product. The question of whether ricin might be turned from a poison into a medicine is one that began to attract serious scientific attention in the 1970s and 1980s, driven by the recognition that the same properties that made ricin so effective as a toxin, its ability to enter virtually any cell and to disable protein synthesis with extreme efficiency, might under carefully controlled circumstances be directed against specific categories of cells that it would be desirable to destroy, most notably the cells of malignant tumors. The concept that emerged from this line of thinking was the immunotoxin, sometimes also called a magic bullet in homage to the language of Paul Ehrlich, who had used that phrase decades earlier to describe his vision of therapeutic agents that would seek out and destroy diseased cells while leaving healthy ones unharmed. A vision that the technology of the late 20th century was finally beginning to make practically achievable. The approach involved chemically linking the ricin molecule, or in many cases only the ricin A chain, to an antibody or other targeting molecule that had a specific affinity for a protein found on the surface of cancer cells, creating a conjugate molecule that would, in theory, bind selectively to cancer cells, be taken into those cells, and then release the ricin A chain to perform its lethal work on the ribosomes, killing the cancer cell from within. The elegance of this concept attracted considerable research attention throughout the 1980s and into the 1990s, with laboratories in the United States and Europe and elsewhere working to develop and test immunotoxins based on ricin and other ribosome inactivating proteins, conducting experiments in cell cultures and in animal models that demonstrated proof of the concept in encouraging detail. The challenges involved in translating this promising concept into safe and effective clinical treatments proved, however, to be substantially more difficult than the initial results had suggested. And the history of immunotoxin research in the decades that followed is in many ways a history of persistent and patient scientific effort in the face of obstacles that required new insights and new approaches to overcome. One of the most significant challenges was the immunogenicity of the ricin protein itself, meaning the tendency of the human immune system to recognize it as a foreign substance and to mount an antibody response against it, which limited the duration of any therapeutic effect and caused adverse reactions in some patients. Problems that researchers addressed through various strategies of molecular modification aimed at reducing the immunogenic profile of the ricin component without compromising its cytotoxic activity. Another significant challenge was the question of selectivity, because even when immunotoxins were designed with highly specific targeting components, the practical achievement of selectivity in the complex environment of the living body proved more difficult than it appeared in experimental systems, and the potential for off-target toxicity in normal tissues remained a concern that had to be carefully addressed in any clinical development program. Over the next several decades, the field of immunotoxin research matured considerably, and by the early years of the 21st century, several immunotoxin-based drugs had successfully navigated the clinical development process and received regulatory approval for use in specific cancer indications, representing the fulfillment, at least in part, of the therapeutic vision that had inspired the field's founding researchers. It is worth noting that the ricin-based immunotoxins, while representing an important branch of this research tradition, were not among the first to reach clinical approval, partly because of the immunogenicity challenges, and partly because other ribosome inactivating proteins with somewhat different properties were in some respects more tractable for clinical development, a circumstance that did not diminish the foundational importance of ricin research to the entire field, but that meant the specific path from castor bean to approved cancer drug was a longer and more complicated one than researchers of the early 1980s might have anticipated. And through all of this work, conducted in quiet laboratories, in academic medical centers and pharmaceutical companies around the world. The fundamental biochemistry that Peter Hermann Stillmark had first observed in his Dorpat laboratory in 1888 remained constant. The same protein performing the same molecular action that it had always performed, its properties unchanged by the passage of time or the accumulation of human knowledge about it. The decade of the 1990s brought changes to the geopolitical landscape that had important implications for the history of ricin as a subject of both scientific and public concern, as the dissolution of the Soviet Union in 1991 and the opening of the Cold War's frozen archives introduced new information about the scale and nature of Soviet biological weapons programs that substantially altered the Western understanding of what had been happening behind the Iron Curtain during the preceding decades. The testimony of Ken Alibek, a senior scientist and administrator who had worked within the Soviet biological weapons program known as Biopreparat, before defecting to the United States in 1992, provided the most detailed and authoritative account yet available of a program that had continued, and in some respects expanded even after the Soviet Union's signature of the Biological Weapons Convention, with a workforce of tens of thousands and a mandate that included the development and production of agents capable of causing disease and death on a massive scale. Alibek's account, which he eventually made public in a memoir published in 1999 under the title Biohazard, described a program that had weaponized dozens of biological agents, including strains of anthrax, smallpox, plague, and various toxins, and his testimony contributed significantly to the urgency with which Western governments and international organizations approached the question of biological weapons in the years following the Cold War's end. The broader context of post-Cold War biosecurity concern coincided with a period in which the internet was making information about the properties of dangerous substances, including ricin, more widely accessible than it had ever been before. A development that raised new concerns about the potential for non-state actors, including terrorist organizations and individuals, to acquire knowledge sufficient to produce or deploy such materials. The concern was not entirely abstract, as the 1990s produced a small number of cases in which individuals or groups had attempted to produce ricin for use in threatened or actual attacks, cases that varied considerably in their technical sophistication and in the degree of harm that resulted, but that collectively demonstrated that the theoretical accessibility of ricin as a weapon was beginning to translate into practical attempts at its use by actors outside the state security and military research contexts in which it had previously been encountered. The case of the Minnesota Patriots Council, a far-right extremist group in the United States, represented one of the most fully documented early examples of this phenomenon, as members of the group were arrested in 1991 in possession of ricin that they had extracted from castor beans, following instructions obtained through extremist literature, and they were convicted under the Biological Weapons Anti-Terrorism Act of 1989, representing the first prosecution under that statute, and establishing an important legal precedent regarding the treatment of ricin as a biological weapon under American law. Meanwhile, in other parts of the world, security services were becoming increasingly aware of the interest that various extremist organizations were showing in ricin and other biological toxins as potential weapons, an awareness that was reflected in intensified monitoring and in the development of new detection technologies designed to identify the presence of ricin in environments where it might have been deployed or in packages and letters that might have been contaminated. It is worth noting that during this same period, the scientific literature on ricin was growing substantially, driven both by the therapeutic research programs already described and by the growing investment in biosecurity-related research that was making ricin a subject of study for scientists working on detection methods, protective measures, and potential antidotes. And the cumulative body of knowledge about the toxin's properties and behavior was by the mid-1990s and considerably more extensive than it had been even a decade earlier. The convergence of post-Cold War disclosures, the spread of information through new communication technologies, and the demonstrated interest of non-state actors in ricin as a weapon created a security landscape in the 1990s that was, in some respects, more complicated and less predictable than the Cold War landscape that had preceded it, because the threats now came from a wider range of actors, operating across a wider range of contexts, with levels of technical capability that varied enormously from case to case. And as the decade drew toward its close, with the memory of the Gulf War's revelation of Iraqi biological weapons programs still fresh, and with the concerns raised by the 1995 sarin attack in the Tokyo subway system, sharpening the attention of security planners worldwide to the reality of chemical and biological terrorism, ricin's profile as a substance of biosecurity concern was higher than it had been at any previous point in its long and complicated history. The years immediately following the turn of the millennium, and particularly the period following the September 2001 attacks in the United States, and the anthrax letter attacks that followed in October and November of that same year, brought an intensity of public and governmental attention to biological threats that transformed the landscape of biosecurity policy and research in ways that had lasting consequences. The anthrax letters, which were sent to several media organizations and to 2 United States senators, and which resulted in the deaths of 5 people and the infection of 17 others, demonstrated with terrible clarity the potential for a biological agent delivered through the postal system to cause fear, disruption, and death on significant scale, and they created an atmosphere of heightened vigilance regarding suspicious mail and packages that would persist for years. It was within this heightened atmosphere that a series of incidents involving ricin in the United States postal system took on a significance that extended well beyond the specific details of each individual case, contributing to a broader narrative of biological threat that was shaping public discourse and government policy in profound ways. In October 2003, a letter containing ricin was discovered at a postal facility in Greenville, South Carolina, and a subsequent investigation traced the letter to a writer who called himself Fallen Angel and who claimed to be a truck driver protesting proposed new regulations on trucking hours. A case that illustrated the range of motivations that could lead individuals to reach for a biological toxin as an instrument of threatened violence. In November 2003, another ricin letter was intercepted, and in February 2004, ricin was discovered in the mail processing facility that handled correspondence for the White House. And later that same month, additional ricin contamination was found in the Senate office of the Majority Leader, Bill Frist, triggering evacuations and decontamination procedures and attracting extensive media coverage that brought the name of the castor bean toxin to the attention of millions of Americans who might previously never have heard of it. The response to these incidents illustrated both the seriousness with which the authorities regarded the threat of ricin as a potential weapon and the considerable practical challenges involved in decontaminating facilities exposed to biological toxins, challenges that required specialized expertise and equipment, and that disrupted the normal operations of the affected facilities for days or weeks. It is worth noting that none of the ricin incidents of this period resulted in casualties, a fact that reflected both the relatively small quantities of ricin involved and the effectiveness of the detection and response measures that had been developed in the years since the anthrax attacks. And that served as a reminder that the gap between the possession of a dangerous biological agent and the successful deployment of that agent as an effective weapon was, in practice, considerably larger than the simplified narratives of biological terrorism sometimes suggested. The Federal Bureau of Investigation's investigation of the ricin letters, like the prolonged investigation of the anthrax letters that preceded them, consumed enormous resources and illustrated the difficulty of attributing anonymous letters containing biological agents to specific individuals, a challenge that the forensic tools of the era were not yet fully equipped to resolve with the speed that the urgency of the threat demanded. Meanwhile, the public health and biosecurity communities were using the heightened attention generated by these incidents to make the case for increased investment in the infrastructure of biological defense, including surveillance systems, laboratory detection capabilities, stockpiles of medical countermeasures, and the research programs aimed at developing treatments and vaccines for the biological agents considered most threatening. And through all of this period, the scientific community continued its patient work of characterizing ricin's properties with ever greater precision, of understanding its molecular mechanism in finer detail, of exploring the therapeutic applications that had attracted interest since the 1970s, and of developing the detection methods that would allow security and public health officials to identify its presence more quickly and reliably than had previously been possible. Work that was unglamorous in the day-to-day reality of laboratory routine, but that represented the accumulation of knowledge on which any effective response to the threat of ricin would ultimately depend. The development of methods for detecting ricin in environmental samples, in clinical specimens, and in suspicious materials has been a scientific challenge of considerable practical importance, driven by both the biosecurity concerns already described and by the clinical need to identify ricin exposure in patients presenting with unexplained illness. And the history of detection technology in this area reflects the broader trajectory of analytical chemistry and molecular biology over the past several decades. In the years immediately following the Markov assassination in 1978, the detection of ricin in biological samples was a technically demanding undertaking that required specialized expertise and was not readily available outside a small number of research and defense laboratories, a limitation that complicated the forensic investigation of the Markov case, and that pointed to the need for more accessible and more sensitive detection methods. The discovery of the platinum iridium pellet in Markov's thigh had provided the crucial physical evidence linking his death to the assassination attempt, but the detection of the ricin itself required careful analysis of the pellet and its contents at the Defense Research Establishment at Porton Down, using the immunological detection methods that were available at the time and that were sufficient to confirm the presence of ricin, even though the quantity involved was vanishingly small. Over the following decades, advances in immunological techniques, most notably the development of enzyme-linked immunosorbent assay methods, which are commonly known by the acronym ELISA, provided the foundation for increasingly sensitive and specific tests for ricin that could be adapted for use in a range of settings, and that formed the basis for the first generation of field-deployable ricin detection kits. The development of mass spectrometry techniques capable of identifying proteins with high sensitivity and specificity added another dimension to the detection toolkit, allowing analysts to confirm the presence of ricin through its characteristic molecular signature, rather than relying solely on immunological methods, an advance that was particularly valuable in cases where the immunological tests might give ambiguous results due to the presence of related proteins or other interfering substances. It is worth noting that the challenge of ricin detection is complicated by the protein S structural similarity to other components of the castor bean, most notably ricin's non-toxic cousin agglutinin, which shares some immunological properties with ricin and which can cause false positive results in detection assays that are not sufficiently specific to distinguish between the two proteins. A problem that required considerable scientific effort to resolve through the development of assays based on portions of the ricin molecule that are unique to the toxic form. Clinical detection of ricin exposure in living patients presents additional challenges because ricin does not persist in the blood or urine in detectable quantities for extended periods after exposure, and the clinical picture of severe ricin poisoning overlaps with that of other serious illnesses in ways that can make the initial diagnosis difficult without specific laboratory testing, circumstances that have historically meant that ricin poisoning has sometimes been recognized only after a significant delay. The development of more sensitive mass spectrometry methods in the first decade of the 21st century substantially improved the ability of clinical and forensic laboratories to detect and confirm ricin's exposure from biological samples, and these advances were accompanied by the development of reference standards and proficiency testing programs that help to ensure the accuracy and reliability of ricin testing across the network of laboratories with the relevant capabilities. During this period, the biosecurity research programs funded by the United States government and by governments in Europe and elsewhere also invested substantially in the development of rapid field deployable detection systems for ricin and other biological threat agents, systems designed to provide results in minutes rather than hours, and to be operable by personnel without specialized laboratory training. And while the performance characteristics of these rapid systems were generally inferior to those of laboratory-based methods, their speed and accessibility made them valuable tools for the initial screening of suspicious materials in situation requiring rapid decision making. And as the science of ricin detection continued to advance through the second decade of the 21st century and beyond, driven by the steady application of new technologies and by the sustained investment of research resources, the gap between the capability available to investigators of the Markov case in 1978 and those available to their modern counterparts grew ever wider, a progress that brought with it a quiet satisfaction for the scientists who had contributed to it, even as the underlying reason for its necessity, the fact that ricin remained a substance of potential use as a weapon, was itself a source of the kind of sober reflection that such a history inevitably invites. The question of whether a specific antidote or treatment for ricin poisoning might be developed has occupied researchers for much of the period since ricin's toxicity was first scientifically characterized. And the pursuit of an effective countermeasure has followed a path that illustrates both the remarkable progress that modern biomedical science is capable of making and the particular difficulties that attend the development of treatments for a substance that acts by an irreversible molecular mechanism. The fundamental challenge is one of timing and mechanism, because ricin's action on the ribosome is irreversible once the A chain has performed its depurination reaction, meaning that any antidote capable of neutralizing the toxin must do so before the A chain reaches the ribosome and completes its work, and the window of opportunity for such intervention is narrow, particularly in cases of injection where the toxin enters the body and begins to distribute to tissues rapidly. The concept of passive immunization, the administration of antibodies that bind to and neutralize the ricin molecule before it can enter cells, has been explored as a potential antidote strategy since the earliest days of ricin immunology, drawing on Paul Ehrlich's 19th century observations that animals exposed to small doses of ricin could develop protective antibodies, and this approach has been the subject of substantial research investment over the past several decades. Various groups of researchers have developed ricin-neutralizing antibodies, both polyclonal preparations derived from immunized animals, and more recently monoclonal antibodies, produced by the techniques of modern biotechnology, and these preparations have demonstrated effectiveness in animal models of ricin poisoning when administered before or shortly after exposure, a result that has supported the continued investment in this approach, even as the challenges of translating animal model results to human clinical effectiveness have remained substantial. The development of a ricin vaccine designed to induce the immune system to produce its own neutralizing antibodies in advance of any potential exposure represents another strand of research that has received considerable attention from both academic groups and from defense and biosecurity research programs, and several candidate vaccines based on modified forms of the ricin toxoid, meaning forms of the ricin molecule that have been chemically or genetically altered to eliminate toxicity while preserving the immunogenic properties needed to stimulate antibody production, have been evaluated in preclinical and clinical studies. It is worth noting that the specific population for whom a ricin vaccine would be most directly relevant is relatively narrow, consisting primarily of military and security personnel who might be at elevated risk of exposure in the context of their professional duties, as well as laboratory workers who handle ricin in the course of legitimate research. And the size of this target population has implications for the commercial viability of vaccine development that have affected the pace and scale of investment in this area. The development of small molecule therapeutic agents capable of interfering with ricin's mechanism of action at the molecular level represents a third approach to ricin countermeasure development, and research in this area has sought to identify compounds that might block the A chain's interaction with the ribosome, inhibit the cellular uptake of the ricin molecule, or in some other way interrupt the chain of events that leads from exposure to cellular damage, though this approach faces the fundamental challenge of the irreversibility of the A chain's action once it has reached the ribosome. Research into the structural biology of ricin, driven by advances in X-ray crystallography and other structural determination techniques, has provided detailed three-dimensional maps of the ricin molecule and its interactions with the ribosome, information that has been valuable both for the design of potential therapeutic agents and for the broader scientific understanding of ribosome biology that ricin research has contributed to over the decades. The overall picture of ricin countermeasure development as of the mid-2020s is one of meaningful scientific progress, accompanied by the persistent challenges that attend the development of any medical countermeasure for a substance, whose potential use as a weapon creates a market of uncertain size. And while no ricin antidote has yet received regulatory approval for human use, the body of scientific knowledge and the portfolio of candidate products that have been developed represent a substantially stronger foundation for response to ricin exposure than existed at the time of the Markov assassination. And in the quiet collaboration of researchers across institutions and national boundaries, in the patient accumulation of data from cell culture experiments and animal models, and the occasional tragic human case, the pursuit of an effective treatment for ricin poisoning continues. Driven by the same combination of scientific curiosity and practical necessity that has characterized the entire long history of humanity's engagement with this remarkable and troubling substance. The social and cultural dimensions of ricin's history are perhaps less immediately apparent than its scientific and political dimensions, but they are nonetheless real and meaningful, and they reflect the broader patterns through which societies understand and represent substances that carry both extraordinary potential and extraordinary danger. The castor plant itself has occupied an interesting cultural position throughout its long history of human association, valued and cultivated in one context as a source of useful oil, feared and avoided in another, as a plant capable of causing serious harm, and this dual character has given it a somewhat ambiguous status in the cultural imaginaries of the many societies that have known it. In traditional cultures where the castor plant was a familiar part of the agricultural landscape, knowledge of both its useful and its dangerous properties was transmitted through practical experience and oral tradition, embedded in the fabric of everyday life, in ways that integrated the plant's risks into a broader understanding of the natural world as a place of both gift and danger, requiring knowledge and care to navigate safely. The 19th century's scientific characterization of ricin transformed this diffuse folk knowledge into precise scientific fact, and with that transformation came a new kind of cultural representation as the toxin began to appear in the specialized literature of chemistry and toxicology, and eventually in the broader literature of poison, crime, and thriller fiction that drew on the palette of scientific knowledge for its effects. The literature of detection and crime that flourished in the late 19th and early 20th centuries found in poisons, generally a rich source of narrative material and ricin's properties, its extreme potency, its delayed action, the difficulty of detecting it without specialized knowledge, made it an appealing element for writers in search of plausible and interesting methods for fictional homicides, and it appeared in various forms in the crime fiction of the period, though rarely under its own name, and more often as an unnamed or vaguely described vegetable poison. The Georgy Markov assassination in 1978 changed the cultural status of ricin in a fundamental way, introducing it to a much wider audience than had previously known its name and embedding it in a narrative of Cold War espionage that carried its own particular cultural weight, the story of a writer killed by a state that feared his words sufficiently to deploy a weapon of such elaborate technical sophistication against him, representing a kind of parable about the relationship between political power and intellectual freedom. In the decades following the Markov case, Racine appeared with increasing frequency in fictional representations of espionage and terrorism, from thriller novels to film and television productions, and its cultural profile continued to grow with each real-world incident that brought its name back into the news, including the Ricin letter incidents of the early 2000s and various subsequent cases that kept it present in public awareness. It is worth noting that the cultural representation of ricin, like the cultural representation of most dangerous substances, has tended to emphasize its most dramatic aspects at the expense of a more complete picture, and the popular understanding of ricin has been shaped more by its appearances in spy thrillers and news coverage of biosecurity incidents than by the quieter and more nuanced story of its role in agricultural commerce, its contributions to the history of biochemistry, and its potential as a therapeutic tool. The television series Breaking Bad, which aired in the United States between 2008 and 2013, included ricin as a recurring plot element in a manner that brought the substance to the attention of an enormous popular audience, contributing to its cultural familiarity in a context very different from either its historical or scientific dimensions, and demonstrating the remarkable capacity of popular culture to shape public understanding of even the most technically specialized subjects. And in all of these various cultural representations, from ancient folk knowledge to Cold War spy story to primetime television drama, the castor bean and its most extraordinary product have served as a mirror of sorts, reflecting back to the societies that encountered them, the particular anxieties and preoccupations of each era, the fear of invisible poison, the dread of state violence against individuals, the concern about weapons of mass destruction in the hands of non-state actors, each culture finding in this small red mottled seed the specific kind of darkness that its particular historical moment was most inclined to fear. The geography of the castor plant, and by extension, the geography of the global castor oil industry, is a subject that reveals something important about the relationship between the most ordinary aspects of agricultural commerce and the most dramatic chapters of ricin's history, and it is a subject worth exploring with some care as we move through the middle chapters of this long and gently unfolding story. India has been and remains the world's largest producer of castor oil, accounting for the large majority of global production in most years, with the state of Gujarat in western India serving as the center of the country. SS castor cultivation and processing industry, its dry and semi-arid soils particularly well suited to the castor plant's preferences, and its long agricultural tradition providing the knowledge and infrastructure necessary for large-scale production. The castor oil industry in India employs hundreds of thousands of people across the supply chain, from the farmers who grow the plants in fields across Gujarat and neighboring states to the workers who harvest the seeds and the technicians who operate the pressing and refining facilities that convert those seeds into the oil that is exported to markets around the world for use in the production of lubricants, cosmetics, pharmaceuticals, and various industrial materials. Brazil is the second largest producer, with castor cultivation concentrated in the northeastern region of the country, particularly in the state of Bahia, where the castor plant, known locally as the mamona, has been an important agricultural crop for centuries, its cultivation deeply embedded in the agricultural culture of a region that has experienced both periods of prosperity and periods of significant hardship connected to its dependence on cash crops. China, Ethiopia, and various other countries in Africa and Asia also contribute to global castor production, making the castor plant one of the more genuinely global agricultural commodities, grown on every inhabited continent and traded in markets that connect producers in developing countries with consumers in industrialized ones. It is worth noting that the processing of castor seeds into oil necessarily generates the residual seed cake that contains ricin, and the management of this byproduct is a practical matter of some significance for the industry, as the material cannot safely be used as an animal feed without treatment to destroy or remove the ricin, and the various methods that have been developed for detoxifying castor seed cake have been the subject of both academic research and practical industrial development over the decades. The presence of ricin in castor seed cake means that castor oil production facilities are, in a sense, routine producers of a biological toxin in the course of their normal operations, a fact that is well understood by the regulatory authorities and occupational health professionals who oversee the industry. But that is rarely part of the public discourse about a substance that most people encounter only in the form of the processed oil in a medicine cabinet or a bottle of skin cream. The occupational health dimensions of castor oil production have received attention from researchers over the years, as workers in processing facilities can be exposed to dust containing castor allergens and potentially ricin, and the literature on occupational lung disease associated with castor bean processing represents a body of evidence about the health effects of chronic low-level exposure to castor-derived materials that complements the more dramatic clinical literature on acute ricin poisoning. The global castor oil market is connected through trade to virtually every major economy in the world, and the price of castor oil fluctuates in response to the same complex of factors that affect agricultural commodity markets generally, including weather conditions in the major producing regions, currency exchange rates, demand conditions in the various end-use industries, and the availability of competing materials. During this period of the early 21st century, new applications for castor oil in the production of biopolymers and biofuels have expanded the demand for the material and brought new investment into the production and processing sector, a development that has increased the global area under castor cultivation, and with it the total quantity of castor seed cake and its associated ricin content that is generated as a byproduct of the industry each year. And in the fields of Gujarat and Bahia and the other growing regions of the world, the castor plant continues its ancient cycle of growth and seed production, indifferent to the extraordinary complexity of the human story that has accumulated around it, drawing water and sunlight and soil